I welcome all the students of B.Sc 4th semester for this online class. Today we are going to discuss about alternating current and transient circuits. So first of all, we shall start with this what the things that we are going to discuss before going to start about this alternating current. As you know, there are two types of current. One is AC current and another is DC, that is alternating current and direct current. Direct current means in which the magnitude of the current or voltage is held constant and it is in one direction, hence it is also called as unidirectional current. Whereas in case of alternating current, the magnitude of the voltage and current changes with respect to time. So this change may be either sinusoidal or square or triangular or the sawtooth form. So this type of current that we call it as alternating current. So before going to start about this alternating and that is LCR series circuit, so we have to define the some important definitions, that is operator J, organ diagrams, then LCR series circuit, LCR parallel resonance circuit, and under this we can define some important parameters, that is resonant frequency, half power frequencies, bandwidth, and quality factor. So we are deriving the expression for the current as well as the impedance and phase for LCR series resonance circuit using this operator J. So before going to derive these equations, we shall discuss something about this operator J and why this operator J is used and to represent what parameter of a number this operator J represents and the organ diagram. Okay, what it represents, all these things today we shall discuss. So before going to this operator J, I will define the three types of numbers. The first one is real number, second one is imaginary number, and the third one is complex number. The complex number is the combination of real and imaginary number. So we shall discuss this what is complex number. So consider the quadratic equation, that is x squared minus 4x plus 8, that is equal to 0. The roots of these equations that are given by 2 plus or minus square root of minus 4. So this each root of the quadratic equation consists of both real and imaginary parts. The combination of real and imaginary quantity is called as complex quantity. So this roots of this above equation that I can write minus 4, that is square root of minus 4, that can be written as 4 into minus 1, or that is equal to 2 into square root of minus 1. So that is square root of minus 1. So that is represented by means of an j. Okay, the meaning of square root of any negative number reduces to find the meaning of square root of minus 1. For convenience purpose, the square root of minus 1 is usually written as j. So that we call it as operator j. So we shall write the complex quantity or number can be written in the form of x plus jy, that is equal to z, where x and y are the real numbers of the complex number and j is square root of minus 1. Therefore, we can write any complex number as z is equal to x plus jy. So all positive real numbers are represented as points on a line to the right side of the origin and negative real numbers on the left side of the origin. For the representation of imaginary numbers graphically, by drawing a line through origin at right angles to the line on which real numbers are represented. So we can convert this imaginary number into a real number by using this operator j. So 1 into j, that is equal to 1 into square root of minus 1 into square root of minus 1. So that becomes 1 into minus 1. So that is equal to minus 1. So thus plus 1 can be converted into minus 1 by operator j. Thus in the figure we can show that the plus 1 can be converted into minus 1 by turning the 0 1 line through 180 degree. Thus operation of multiplying plus 1 by j square is equivalent to turning the line 0 1 through 180 degree. So multiplying j square is same as multiplying j twice. Hence, multiplication of j only once is equivalent to rotate the line 0 1 through 90 degree. This turning may be either clockwise or anti-clockwise. So thus anti-clockwise through 90 degree is taken as operation of multiplying a number by plus j. The clockwise through 90 degree is taken as the operation of multiplying a number by minus j. Now the plus or minus square root of minus 4 has two roots. So that is plus 2j and minus 2j. So therefore the plus or minus square root of minus 4 may be represented graphically by turning the line 02 through 90 degree in anti-clockwise direction for plus 2j and clockwise direction for minus 2j. For representation of imaginary numbers graphically by drawing the line through origin at right angles to the line on which the real numbers are represented. This gives the two axes at right angles to each other. A diagram on which both real and imaginary numbers are represented is called organ diagram. So thus we can represent the complex number 2 plus 2j may be represented on the organ diagram by OA line shown in the graph. It may be noted that the part of any complex number which does not contain j represented in the direction x-axis and is called as reference or phase component. The part that contains the operator j is called quadrature component. The magnitude of complex number is given by the square root of the sum of squares of reference component and the quadrature component. So with this operator j and organ diagrams, so let us start with this series resonance circuit. So what is this series? Series means the three passive components such as inductance, resistance and capacitor. They are connected in series. So in the circuit I have shown. So for that purpose you have to consider a sinusoidal alternating source of EMF E is equal to E naught e raised to j omega t applied to the series combination of L, C and R as shown in the circuit. The total vector impedance of the combination is sum of three parts, that is the R due to the resistance R, J omega L due to the inductance coil L and 1 over J omega C, that is equal to minus J divided by omega C, because that J can be written as J minus J upon omega C due to the capacitance C. So you have to represent the, because the current is not in phase with the voltage in case of L and R, L and C. Only in case of resistance the current is in phase with the voltage, whereas in case of inductance and capacitance they are not in phase. In case of inductance the current is always lagging by 90 degree with respect to voltage. In case of capacitor, the current is always leading by 90 degree in with the voltage. Hence this we can take it as an imaginary. So we can consider the vector form of the EMF equation. So that once again the Ohm's law, that is R into I, that is total impedance into the current flowing through that impedance circuit, that gives the voltage drop across that combination. Accordingly, we can write equation number 1. So equation number 1 represents the vector form of the equation, where I is the instantaneous current in the circuit and is given by, that is I is equal to that E naught e raised to j omega t whole divided by that bracketed quantity. So that is equation number 2. So 1 divided by that bracketed quantity, we can, to this factor or to this quantity, we can divide and multiply by that r minus j into bracket omega l minus 1 over omega c. So on multiplying and dividing by this, so go on simplifying this equation. So finally we will arrive that equation number 3. So that equation number 3 can be written as alpha minus j into b. Okay. So and alpha and beta, they are defined. Okay. So with this, if we put this tan theta, so along this x-axis that you have to take r, and along y-axis, because they are imaginary quantity, so omega l minus 1 over omega c. So that is shown in the figure, and the total impedance that is given by square root of r square plus omega l minus 1 over omega c whole raised to square. So that we can write from that figure, that is we can write tan theta is equal to that opposite side divided by hypotenuse. Opposite side is omega l minus 1 over omega c, whereas this adjacent side, that is equal to r. So tan theta is given by this equation, and cos theta, you can, from that figure we can write cos theta and sin theta values. So with this equation number 3 reduces to, that means on defining this tan theta, cos theta and sin theta, that equation number 3 is reduced in this form, that becomes cos theta, that 1 divided by square root of r square plus into bracket omega l minus 1 over omega c whole raised to square into cos theta minus j sin theta. So therefore we can write this cos theta minus j sin theta is as e raised to minus j theta. Okay. Substitute this value in that equation number 2 and simplify it. On simplifying, the expression for the current, that I is equal to that E naught divided by square root of r square plus into bracket omega l minus 1 or omega c whole raised to square into e raised to j into bracket omega t minus theta. So this quantity E naught divided by that square root quantity, that gives I naught. So therefore I can write the expression for the current, that is given by the equation number 5, that is equal to I, that is equal to I naught into e raised to j into bracket omega t minus theta, where I naught is given by this expression. So that is equal to E naught divided by z, and z is equal to square root of r square plus into bracket omega l minus 1 over omega c whole raised to square. So therefore we can write the peak value of the current, that is equal to I naught, and z is the total impedance of the circuit, which is the ratio of peak voltage to the peak current. The impedance of the circuit is given by the theta, that is phase angle, that is given by theta is equal to tan inverse that omega L minus 1 over omega C whole divided by R, where omega L is the reactance of the inductance, 1 over omega C is the reactance of the capacitor. So to on taking these XL and XC, we can write theta is equal to tan inverse into bracket XL minus XC divided by R. Thus, the total impedance of the circuit, which is the ratio of RMS voltage to the RMS current. Okay. So from equation number 5, it is clear that current is lagging by an angle theta with the applied voltage. Hence, the angle is given by theta is equal to tan inverse XL minus XC whole divided by R. So, all these, the current, voltage across inductance, voltage across capacitance, voltage across resistance and their direction, and the current direction, total current that is flowing through the circuit, that magnitude and direction, so that is represented by that figure which is shown in the figure. Next, we shall discuss some special cases of this series resonant circuit. If omega L, that is reactance of the inductance, is greater than the reactance of the capacitor, that is XL is greater than XC, the potential difference across L is greater than the potential difference across C. Now the voltage leads the current by angle theta. Circuit is inductive circuit. Angle between the voltage and current that is given by, that is theta is equal to tan inverse into bracket omega L minus 1 over omega C whole divided by R. So the current is lagging by an angle theta with the voltage. Next, the second special case is if omega L is less than 1 over omega C. What it implies? XL is less than XC. That means the potential difference across L is less than the potential difference across C. Now the voltage is lagging the current by an angle theta. Hence, this circuit is called as capacitive circuit. Angle between the current and voltage is given by, that is tan inverse 1 over omega C minus omega L divided by R, or that is equal to tan inverse XC minus XL whole divided by R. That means the current is always leading by an angle theta with the voltage. Now the special case, the third special case is if omega L is equal to 1 over omega C, that is XL is equal to XC. The reactance of the inductor and capacitors are equal, hence the voltage across them are equal but they are opposite. Therefore, the theta is given by tan inverse omega L minus 1 over omega C divided by R, or tan inverse XL minus XC upon R. So, since XL is equal to XC, so that becomes tan inverse 0 by R. So, that is always 0. That means theta is equal to 0. This implies that the voltage and currents are in phase. The potential difference across the inductor and capacitors are equal but opposite. Hence, they cancel each other. The impedance of the circuit, that is Z is equal to R. The circuit is pure resistive circuit. Then the current in the circuit depends only on the resistance and is maximum and is given by, that is equal to E naught by R. That because omega L, that is equal to 1 over omega C. The frequency at resonance is given by, so that is omega R into L, that is equal to 1 over omega R into C, or that you can write omega R square, omega R whole raised to square, that is equal to 1 over LC. So therefore, on simplifying that, the resonant frequency FR is equal to 1 divided by 2 pi square root of L into C. This series resonant circuit is called as acceptor circuit because at resonance the impedance is minimum and that is equal to R. Hence, the maximum current is flowing through the circuit at resonance. Hence, it is called as acceptor circuit. That means it accepts current at resonant frequency. That means the series resonant circuit accepts or it allows the current at a natural frequency of the circuit. That means natural frequency is resonant frequency of the circuit. But the current decreases for other frequencies, hence it is called as acceptor of filter circuit. So with this we shall conclude the today's lesson. In the next class we shall start with this resonance. What is resonance and resonant LCR circuit? Next, parallel resonant circuit and bandwidth, then resonant frequency, then half power frequencies F1, F2. All these things that we shall discuss in the next class. Okay.